going to move on now with the June recap. Let's go over that.
I thought that's what we were doing.
Yeah, but this is the specific part related to physics. Okay, so what did we cover? Primarily quantum mechanics, okay? And we talked about computers. If you can touch it, if you can see it, it's not called quantum. It should not be called quantum. It's called classical, okay? And so what these people say, oh, we have a quantum computer. What do you mean by quantum computer? You mean there's something I can't touch or see in the quantum computer? No, they say we looked at all these phenomena, and we saw decoherence, we saw entanglement, we saw superposition, and we know how to manipulate it. Yeah, you know how to manipulate it for technology, but you don't understand it. Why do you call it a quantum computer when it's a classic? The classical part is the one that you can touch or see. The intangible part, the one that you call quantum, you can't explain it. So what's the point? Just the saying that I saw this effect and I applied it to technology and I made this computer which is faster or whatever, right? Is that why we call it a quantum computer?
It sounds better than classical computer.
Yeah, because if you say classical, people say, oh, you're still in the 19th century.
I'm sure the marketing guys got in on the quantum computer. I can sell that.
Yeah. Then you have, we went over the measurement problem. What is that? Well, how and whether wave function collapse occurs.
What is this?
Again, that's the measurement problem. It's called the measurement problem in quantum mechanics. It's whether, if and when, right, wave function collapse occurs, and the inability of the observer to see this collapse, right, directly, has given rise to many interpretations of quantum mechanics. You have the Copenhagen interpretation, which was championed by Bohr and Heisenberg and Born and a couple others. Many worlds, Hugh Everett came up with that nonsense that for every step you take, you branch off on a different universe. That's the explanations they give to the wave function collapse. Hidden variables, championed by Bohm and others. Again, that I think, well, Einstein also was, and Podolsky and Rosen, they were also behind this hidden variables interpretation. They say there's stuff that we do not know about the particle. So the particle itself has properties that we're not aware of.
What is the measurement problem?
Well, the measurement problem is there. How or whether wave function collapse occurs.
Wave function collapse?
Well, that's when you have this wave, and it's a function, it's an equation.
Yeah.
And when the equation collapses, it turns into a particle.
What do you mean the equation collapses?
Yeah, that's exactly what I mean. The equation collapse, that's the way they...
Like you crumple the paper up?
Kind of like that, but you're taking this concept, this abstract concept, which is a wave function, not the wave, but the function that describes the wave, and the function collapses. And they call the wave function...
Why do they need to do that?
Because they need to give a physical interpretation to what happened. How can we summarize it? Very simply.
I feel bad roasting you for this when you're trying to parrot the explanations of another.
Yeah, let me put you back in here for a second. This is the issue. This is summarized like this, and it's not my summary, it's someone else's, okay? And that's that, what is light? Well, it says light travels as a wave and starts off and arrives as a particle. That essentially summarizes the measurement problem, and it's got to do with complementarity, the principle of complementarity that Niels Bohr came up with. That means that the light is both a particle and a wave. The electron is both a particle and a wave. What do they mean by that? They rephrase it in a different way. They don't say it is, they say it behaves as. Okay? And they think with that they got away with saying what it is. And what they're really saying is that light and the electron are both have wave and particle properties. The wave property is only when it's traveling. And at beginning, at source, and at target, that's when it converts into a particle because the wave function collapses to a particle. It's like this elongated thing suddenly from the whole universe. Remember in the case of the electric field, as soon as you measure it, the field extends throughout the universe, all the way to the edge of space-time, and suddenly it collapses to a point.
Locally. So that you can measure it.
Yeah, no, or it's the other way around. When you measure it, it collapses.
Well, that's very accommodating.
Yeah, it is, because now you touched it in some way. They don't know why. Now you looked at it, now you touched it. Now what happens, the whole universe of that specific thing that you're measuring, whether it's the photon or the electron, suddenly collapses from this elongated thing that stretches throughout the universe to a localized point. And you ask, okay, no problem. What's the mechanism? And they say, let me show you some math. We can explain it mathematically.
Oh, because they have some clues in the math, and then they give these...
Extrapolate them.
Yeah, extrapolate.
They just extrapolate because they have to give a physical interpretation. Why? Because otherwise their math would be irrelevant.
Yeah, no one cares about it.
If you can't relate the math to the real world, to physics, what was the point of doing that math, that exercise, and say, oh, look, here's an equation. We have this tautology. Yeah. This side of the equal sign equals the other side of the...
It's a fun puzzle, maybe. But
yeah, like, but then what does it have to do with reality? Okay, so continuing here, here we have the quantum dot technology, okay, also. Under the influence of light, electrons are excited and quantum jump okay, up to a higher energy band and also lower. So this electron goes up and down, and what it does, they look at how much it jumped, and it's a measure of the energy that the quantum dots, they create these dots physically, again, classical stuff, because they're moving molecules around, they are able to concentrate them, and because of the structure of that molecule, because of its shape, and also because of the energy level, it emits a different color light, and they play around with that, and that's why they can give you a sharper color that supposedly replaces some of the older technologies. Again, it's got to do with technology, this quantum dot. That's not the issue. The issue we want to understand is, how does it do it? And for that, you got to go at the atomic level, because if you're going to talk about an electron that's jumping from energy levels for example, from the valence band to the conduction band, which is where they say this occurs between those two levels, then the question is, fine, great.
These are different levels away from the proton?
Yeah, that's all it is, essentially. So you have, essentially,
Different
the conduction level really has nothing to do with the atom, because the atom ends at the valence band. That is the atom. What continues after that is known as empty space. And so what these people are saying is that the electron jumps from the valence band, from its outer electron shell, to no man's land, meaning now it's in the conduction band. Now it's free to move around, and that's why we call it the conduction band.
No longer in the atom.
Right, because now it's part of electricity. Now I can move anywhere it wants. And you say, fine, oh great, I'll concede. What is the mechanism? What makes it jump? And they talk about energy levels and give you the mathematical equation. That's not what we want. That's a description. I want to know the mechanism. And before we can get to that, I need to see your atom and find out why that electron doesn't fall to the center, to the nucleus, or why doesn't it spontaneously fly away, drift away? Well, what keeps it in the valence band? What keeps it in the closer bands to the nucleus? Why doesn't the electron just fly away spontaneously?
Obviously, if the electron's jumping, it's got legs, right?
Yeah, I think
jumping up and down off of the proton.
Well, here you see it. Okay, there it is. That's the model. You have a photon come in there, energy, whatever they call it, and when it does, it hits it into a higher level. And then when the electron loses energy, it falls to the lower level. Great. Okay, so we're talking about energy. Whatever energy is, it gains and loses energy.
Wiggly arrow.
Yeah, but that's the energy.
Yeah, wiggly arrows.
Yeah, and so what is all that nonsense? I mean, why doesn't that electron fall spontaneously to the center of the atom, which is the nucleus? Because the nucleus has the positive protons, the electron is negative, it should fall directly to the nucleus.
There's something keeping it away, but not so away that
it flies away. And so the question is, what the hell is that? I need to see your atom before you can tell me your theory. But to say that it does so, it's a description. So far we have nothing. I need to see your atom so that I can follow your theory. Why it doesn't do that?
Real quick,
or does it?
Real quick, does valence jumping happen instantaneously without time?
Yeah. Well, valence. What do you mean, valence to conduction band?
When the electron jumps.
And what about that?
It's instantaneously.
Yeah, because that's the other issue. The instantaneous you can explain with a rope model, because you have a balloon that expands and contracts. So the edge of the balloon suddenly changes to a smaller level, and then it expands again. So now you can explain this quantum jump very easily.
Did they ever film the frames between the jump?
No, they can't. They can't even see at that level. That's the point.
Are we just talking about crappy technology that can't measure it?
No. They determined that. Niels Bohr determined that in 1911. That he explained it supposedly. Gave a description. He didn't explain it. He just gave a mathematical description that there's a different amount of energy at different levels, and he was able to explain, for example, the spectrum of hydrogen with that, and that's why he got his Nobel, and that's why he was regarded as a god. But the issue is he's got no explanation to this day. We don't know what the mechanism is for that. You can't use the word energy, because energy is a concept. We need a physical object. We need to see how the atom really works in there, and that we don't have even to this day.
You can use the word energy if you give it shape and contour and tell us what it looks like and what it's doing, I guess.
Okay, and then from there we move on to what is this? To incoherence, I call it. It's called decoherence. What is that? The loss of information to the environment. There's interference, essentially, from the environment to whatever quantum phenomena occurs. And so they say it's either entangled, or there's superposition, or it could be decoherence. Any of those. No, there's another one. Which one did I miss? Decoherence, entanglement, and superposition. Yeah, those three can happen, and they don't know how it happens. They just say there's interference, especially that last one, entanglement, which means there's action at a distance without any mediator. That's called magic, because if you cannot explain that, you don't have a mechanism, meaning you're just putting angels and spirits in there. Why does, and here you have an example, okay? there we go. Okay, here you have one particle on the other side of the universe. This is what they tell you, okay? One particle on the other side of the universe is going counterclockwise. This one's going clockwise. And now when one changes to clockwise, the other one changes to counterclockwise instantaneously on the other side of the universe. So if you have one top here on Earth and another one on the moon, this top, a discrete top, can affect that top over there.
Could we have really good phone signals if we use that technology?
Well, the issue is not
instantaneously.
Yeah. The issue is that we are aware of the technology that you can use this effect to do technology. What we don't have today,
is an explanation.
For
why
this.
They do that.
You get the right one?
No.
Yeah.
We're still doing the right.
So the issue is we don't have an explanation for all that, and
Or
that's what physics is about. If you don't have an
I'm sure we
explanation,
have explanations.
No,
but
we
good
don't.
ones.
Well, yeah, I mean irrational ones, because all of them rely on concepts, mathematical concepts, meaning all these mathematicians who took over so-called physics, okay, mathematical physics, what they do is they come up with their equations and they use words which represent equations: force, mass, energy, time, all these things that they use to bend, like they bend time, they move the end, they transfer energy, they move the mass. There are no such physical objects.
Semantics, essentially.
But yeah, it comes down to semantics. What they've done is they've turned they reified all these concepts and they start moving them around, and you think they're giving you a physical interpretation when in reality they haven't done anything. All they did was give you a description, which they converted their math into physics, and it's like they go, oh, the X moves this way.
Close enough.
We kick the Y over there, and so
you know what we mean, right? If you don't go to school.
Yeah, we don't have a mechanism. We don't know how the universe works at the micro or macro level. Remember, macro level we have bending of time for gravity. What the hell is that? What do you mean bending of time? What do you mean warping of time? Gravity warps time. A concept warps another concept. What kind of talk is that? That's just semantics.